So today is my last lecture on dynamical systems. So as always, let me just tell you what we have covered so far. So we covered phase space, trajectories on phase space, geometric way of thinking about differential equations. And if you have a differential equation like du dt equal to f of u, then how to find fixed points. Okay, so hopefully all of you remember that a fixed point is when du dt equal to 0. So when f of u equal to 0. So basically find u star such that f of u star equal to 0. That's the way to find a fixed point, right? And then we looked at stability. So we found that the slope of fu at u equal to u star tells you whether a small change from the fixed point will take you back to the fixed point or will take you away from the fixed point. So in particular, if df du at u equal to u star is negative, that means it's stable. That is a small change. So if you make u star plus delta u, this will go back to u. Okay. On the other hand, if it is positive, then it is unstable. Okay. Then we looked at bifurcations, and we found that in one dimensional systems we have three. So we had the transcritical, where you just exchange stability of two fixed points. So a stable fixed point becomes unstable, unstable fixed point becomes stable at the critical point. We had saddle node, where a stable and an unstable node or a fixed point collide and annihilate each other. So if you look at it from the other point of view, so subcritical is typically shown as this. So one of the solutions is, let's say, goes like this, and then from here it becomes stable, whereas the other solution which was stable up to this point after the collision becomes unstable, right. Okay, in saddle node you have let's say at this point magically almost a stable and an unstable node emerges from out of nothing. So this is basically your parameter r, okay. And then you have pitchfork, which was, if this is r, then here the solution, fixed point solution, suddenly becomes unstable, and you have the emergence of two stable fixed points separated by unstable fixed points, right. And we found that we can write normal forms for each of this, okay. And then we had an example of imperfect bifurcation or catastrophe. Okay. And in particular we saw how this can give rise to discontinuous transitions at some portion and continuous transition in another portion. And so we saw examples of pest outbreak, okay. Then basically dog behavior, fight or flight, okay. And we saw that this is also related to the pressure, volume, temperature diagram of a liquid vapor system. Okay. And then last day we started on 2D systems and we looked at linear systems. So, in general you now can write it as du dt equal to au plus bv and dv dt equal to cu plus dv. Okay. And so, therefore, you can write down the slopes of these as the matrix A, B, C, D, and it has 2 eigenvalues, and we saw that by looking at trace of this matrix and determinant of this matrix, you can actually figure out that these will be saddle points, these would be unstable spirals, this would be a stable spiral, sorry, what am I saying, unstable node, sorry. This will be a stable spiral, this would be a stable node. And what is this line? So, we found that this was trace j whole square equal to 4 determinant j, that curve. Everybody remember all this? Any questions about this? Okay. And we illustrated this with Romeo Juliet dynamics, and we saw different styles of romantic relationships. Okay. So, that is how we illustrated all this. All right. So, today in the last class we will be dealing with the really exciting stuff. This is, first we will work with 2D nonlinear systems. Okay. So, what does nonlinear mean? I mean, when I say that something is nonlinear or a differential equation is nonlinear, what does it mean? What will happen to, so why do we say this is linear, and then what would be the difference now that we have a nonlinear? Yeah. So, there will be some u times v or u square or u raised to the power or u raised to the power something times v raised to the power something kind of terms, right. And so, now what you will find is that superpositions of solutions is no longer a solution. So, this breakdown actually results in very exciting things. Okay. Superposition of solutions are not also solutions. See, one of the great properties of linear systems is that if you have solutions, then linear combinations of those solutions are also themselves solutions. That is no longer true for nonlinear systems. Okay. So, let us start with an example, and I will use something which might be known to most of you. This is the Lotka-Volterra prey-predator system.
Excuse me, sir.
Yeah.
Just a small interruption, but intuitively to a person who hasn't done any math or any science whatsoever, how would you explain what nonlinear means? Because I was trying to explain about your lecture to my father, and I was struggling with explaining it without math.
Okay, if you want to use it in one sentence, and I have actually done that in a few public lectures, to use the words of the famous Amitabh Bachchan, ये वो है जो दो और दो पाँच बना दे. Okay, I know again this is a very dated movie reference, but I'm sure your father will get it. Right? But if you want to be more serious, if you want to go in depth, you have to take an example. Okay, and hopefully the example I'll talk about will help you illustrate to your father what nonlinear dynamics is. Okay, so this is the Lotka-Volterra model because two people, Alfred Lotka, who was a chemist but also a pioneering mathematical biologist from US, and Vito Volterra, who was a mathematician in Italy, independently came up with this, but in completely different context. So Alfred Lotka's context was, if you have, let's say U is the concentration of some chemical, V is the concentration of some other chemical, right? And U essentially causes the further production of V. V on the other hand causes the decay of U, and U has autocatalysis, so that is, it results in its further production, whereas V essentially has a decay term. Okay, so if you leave V to itself, it will just decay away. Okay, so if you have this kind of a reaction, what kind of behavior would you expect? Okay, so that's what Lotka was trying to do. It was in the context, specific context of chemical reaction that he was trying to study. Volterra was looking at it in a completely different context, and the story goes, and if you want to read up this story in more detail, I suggest you look up this wonderful book by Carl Sigmund called Games of Life. So Carl Sigmund is, I think he's in the University of Vienna, and he's written this wonderful book on game theory as applied to evolution. So, but the Games of Life is basically a popular science book on ecology, population dynamics, games, stochastic processes, and so on. So, it's a very, very nice book. So, the story goes something like this. So, Vito Volterra's daughter Lucia was engaged to an up and coming field ecologist called D'Ancona, who himself is actually quite famous. So, he is a field biologist, field ecologist, and apparently in one of those occasions where Lucia was taking too long to dress, D'Ancona and his future father-in-law started talking, and as is wont when scientists talk, they start talking shop. And so Volterra asked D'Ancona, so what are you working on these days? Okay, we assume that something like question that was asked, and D'Ancona told him, look, my future dad-in-law, this is the problem. So I'm working on looking at how the fishery population of the Adriatic Sea is changing on the time scale of decades. Okay, so what is it doing? So pardon my map drawing, it's been ages since I last drew these things. So this is the boot of Italy, okay, and this is the Adriatic Sea, okay. So this is the Balkans, so Greece would be down here, okay, and what is the period we are talking about? So we are talking about sometime towards the late 1910s. So this is after the First World War that we are talking about, okay. So what D'Ancona did was he went to the fishing ports of Venice, Fiume, and Trieste. So these are all ports on the Adriatic Sea, and he asked to do a sampling of how much fish of each type there is in this Adriatic Sea and how it changes from year to year. Since he can't do a census, what he did was he went to the fish markets of these places and just asked to see the logs of all the boats, fishing boats, which came back and then basically logged in their catch. So from there he will get an idea of how much of each type of fish was caught, and assuming that the number of fish caught is kind of proportional to the actual population of these fishes, he would get some kind of a sense of what were the ratio of the different fishes, right. So let's suppose in the broadest category he is looking at large predatory fishes. Okay, so things like sharks, okay, rays and so on, and then the prey of these kinds of fish. Okay, so what the sharks feed on. Okay, this is the broadest category, right? And then he is asking, how does the relative fraction of these fishes change from, let us say, 1900 to, let us say, the 1920, okay, which is the time when they are talking. So what he found was something like this. Okay, so this is year, and this is related to the fish population, proportional to the fish population. So if you look at the prey fish, it is going something like this. And there are fluctuations, but roughly this. And the predator fish goes something like this. Okay, so this is predator and this is prey. Sorry, I should have used my blue color. Okay. Now, what are the years we are talking about? So, the period where you see this dip in prey and the rise in predator is the period 1914 to 1918. Anything special about that period? Yeah. So, this is okay. And what D'Ancona was surprised was how on earth does what is happening in the human sphere have a reflection in the relative ratio of the fishes. So, why is it that predator fishes rise up during times of war? I mean, it is not just the spirit of the times, is it? Okay. And he was very puzzled by this, and he told Volterra. And so Volterra, as would be typical of a mathematician, decided to use mathematics to do this. So he said, okay, let us assume that U is the prey fish and V is the predatory fish populations. Okay. Now, the prey fish are getting born with some rate, let us call it RU, but they are also being killed by the predator fishes. So, what would that term correspond to? So, each predator fish is, let us say, killing some B fraction of the prey population available to it. Okay. So, it will be minus BU, but you also have to consider that this is just for one predator fish. So, if there are V predator fishes, so there will be times V. So, it would be something like minus BU, which is the per capita consumption by each predator fish times the predator fish population. Everyone with me so far? So, this basically captures with what efficiency are they killing the prey fishes, this B factor. This includes actually a lot of biological details, like how long are they spending searching for the fish and so on. So, if you are ecologist, you are going to spend a lot of time just disentangling all the factors which go into B, but from a mathematician's point of view, it is some factor, it is some proportion of the prey fish which you are eating. Everyone with me so far? Okay. What about the predator fish? So, the predator fish, in the absence of any prey fish, will just die out, okay, because their source of food is gone. So, in the absence of any prey fish, you will have some death rate into V minus dV, they will just exponentially go down. But what causes them to maintain their population or maybe increase their population is the fact that they are feeding on the prey. So, exactly like this, but now you will have a positive term, okay. So, it will be say BUV, but you need to multiply something here epsilon, because what are you talking about here? It is the predator population. Now, the biomass of prey fish you eat is not completely 100% converted into predator fish, because some of it will go into just repairing your body, swimming about and so on. So there will be some small fraction epsilon which will convert the, which is the fraction of the energy they consume in terms of prey fish into producing children, which is what is contributing to V. So let us take the product of epsilon and B and turn it into a single number called C. Okay.
Is the D a function of U?
Why do you say that?
Because it should depend on the number of prey fish in the population. Right? If U becomes 0, then only that term will dominate.
No, but you can take it, you can just say this is the lifetime of this predator fish, and in the absence of prey fish, it's just basically killing them off. Okay, but in the presence of prey fish, they can feed on them and basically stave off the day of reckoning till much later. Okay.
So can you explain the first equation again?
The first equation.
Yeah.
So this is just your, in the absence of this is basically saying that the fish population, the prey fish population is just increasing exponentially, because their food is not other fish but let's say planktons or whatever. Okay, I mean that food source is not explicitly modeled here. It's just assume that that food source is available at constant quantities. So we could have just put a k minus u term, but for the moment we are just saying that the check on their population is maintained by the predator fishes. So long before they go off to infinity, the predator fish will eat them up.
Will only the population will only increase based on the prey population. There's no intrinsic increase like
The predator fish, yeah, because for the predators can't eat what you call the krill or the planktons and so on. They have to depend on this prey fish. So it's like tigers. So if you have a model in which you have, let's say, some herbivore and tigers, so the herbivores can just eat grass. So if I don't model the vegetation dynamics explicitly, we'll just say grass is roughly a constant, and the herbivores basically grow as a result of eating this grass. Okay, so we can take this to be the growth, but then the tigers can only eat these herbivores, and so they cannot eat grass, and at least it will not help them to survive. And so in the absence of the herbivores, they will just go down in population. Sorry?
The predator fish also have a bird.
Absolutely, and that is actually included in that epsilon I told you about. So I'm just
Depend on the prey fish, the bird.
no, but the birth can only happen if they have enough food, right? And so all of that is kind of lumped into here. Okay. So as I said, each of this B and C has lots of terms inside them, which I'm not disentangling. Okay. All right. So and he said, voila, I have solved your problem. Can you see that? How he solved the problem of the inequality? Okay. So let's look at it this way. What are the fixed points? That is the equilibria of the system. There are two equilibria. One is the trivial equilibria, u star equal to 0, v star equal to 0. Okay, so if you plug in 0, 0, 0, 0, 0, it's trivially 0. But there's another one. So you could set Ru equal to BUV. So this is one. So for the second one, you just say that R u star equal to B u star V star. So since u star is not equal to 0, I can basically just say, oh, that means V star equal to R by B, and similarly from here I get C u star V star equal to D V star, and again since V star is not equal to 0, I can cross them out and I get u star equal to D by C. Okay. So this is the second. So if I plot my phase space, this is 0, 0, and this is my D by C, and R by B. Sorry. Okay. Now, I can do stability analysis, okay, and ask what is the stability of this. So, how will you do the stability analysis now? So, now you notice that J would be, what will it be, the first term? So, the first term, so if I call this f of uv and this to be the g of uv, the Jacobian now becomes the partial derivative of f with respect to u. This will be partial derivative of f with respect to v. This will be the partial derivative of g with respect to u, and this will be partial derivative of g with respect to v. Okay, evaluated at u equal to u star, v equal to v star. For linear systems, u and v were not appearing because when I take the partial derivative they go away. But now for nonlinear systems, this u and v's will appear, and so those u and v's have to be replaced by the corresponding fixed point values. Okay, so let us see, what will I get? R minus BV, yeah. So let us call this V star. Okay, then minus B U star, then C V star, then
U minus U star minus D.
V star minus D. Okay, sorry, C U star, yeah. Okay. Now, for U star equal to 0, V star equal to 0, my J becomes, so J at 0, 0 is R 0, 0 minus D. Okay. So, R is positive, D value is positive, so minus D would be a negative number. Okay. So, now I can just evaluate my trace. So, trace is R minus D and determinant is minus RD, right. So, what is that? Remember, look at here, what will it be? It is a sample, right. So, you can't stay at 0, 0, you will be going away, right. Okay. Now, let us see what will happen if you have U star equal to D by C and V star equal to R by B. Okay. So, now it will be R minus BD by C, sorry, R minus BR by B, which is 0. So, this non-trivial part would be 0, okay. Then minus BU star would be minus BD by C, then CV star would be RC by B, and what will be this term? C into D by C, which is D minus D, which is 0. Okay, so now trace J equal to 0 and determinant J is R B C D by B C, which is simply R D, okay, and R D is positive, which is, so determinant is positive, trace is 0. What is that? Center, right. So, I told you that if there is no real part, you get basically oscillations about the fixed point, right. So, basically that tells me that I will have essentially centers about this, okay. Now, how did it solve d'Ancona's problem? So, what Volterra said was that what's happening in First World War? In the First World War, you have very little fishing going on because so little bit of history. So, Trieste was actually the part of the Austro-Hungarian Empire, and so they belonged to an enemy country. And although this was a secondary theatre of war in the First World War, the fishing fleets could not get it out to sea because the Italian Navy and the Austro-Hungarian Imperial Navy were at war here. Okay. So, essentially fishing is down. Okay. In other years, what was the situation? You had fishing fleets going out. How would it affect that? So, if you have fishing, what will happen? Yes. And what about death rate? Death rate would also affect it because now you have a higher death rate because of the fishing, right? So, I can write it that during non-war, so basically I could say that I can neglect almost the effect of, you can't neglect it of course because you are sampling, right? But you could say that compared to the First World War years, so let us say this is like what's happening in World War I, whereas in the non-war period you have something like du dt equal to r minus, let us call it delta or rho rather, r minus rho. So, the effective growth rate is reduced because of the fishing fleets minus buv, and dv dt is equal to cuv minus d plus delta. So, the death rate is increased because of the fishing v. Okay, so, that is the difference. And so, now what is the non-trivial fixed point? Can anyone tell me? So, u star will be, so d has become d plus delta, and what will be v star? R minus rho by b. So, now what you see is, sorry, what was rho? Rho is the additional, the decrease in birth rate of prey fish because of fishing. Okay. And delta is the additional deaths in predator fish because of fishing. All right. Okay. So, now this is the non-war, so this is during the non-war period. So, if I think of this as my equilibrium of the prey, so this now becomes d plus delta by c, whereas this is just, this is just d by c. And for the predator fish, this is r minus rho by b, whereas this is just r by b. And similarly, this is d plus delta by c, r minus rho by b. Okay. So, even if this delta and rho does not go to 0, you can easily see that since delta and rho are both positive values, as they decrease, this quantity will start going down, and as rho starts going to 0, this will start going up, right. So, using a almost trivial model, Volterra managed to solve a problem which was stumping d'Ancona for a very, very long time. So, this shows you like how much power even a little bit of mathematics can have. Okay.
So, won't CUV also change? It should go down, right?
No, because you say that if predators still have to live, right? So they will still have to keep fish looking for prey and eating them and so on. Huh?
But there's less prey now.
No,
Also.
but see that's factored in the U.
In the epsilon.
C only says like with what efficiency they are killing the fish which are already there. Okay. So then you are saying that fishing interferes with their hunting activity. If what you are saying is true. Okay. So we assume that the hunting activity itself is unaffected. All that it's happening is that it's lowering the growth rate of the prey fish and increasing the death rate of the predator fish. This is very simplistic, but this is just to show like a little bit of mathematics can go a long way. Okay. Now, I told you, right, that if you are planning on talking to an ecologist, never ever even breathe the word Lotka Volterra. Okay. Last you will hear from the ecologist, and that's because there is a lot of unrealistic assumptions here. Now, the first unrealistic assumption is of course the simplistic assumption that in absence of predation the prey fish is just going to explode. Okay. So that you can take care of very simply by saying so du dt equal to r into u in times, and you put in a carrying capacity. So you say that okay, eventually even if there is no prey fish, you will reach some kind of a saturation. Okay. But that is actually not so serious, because you could always argue that long before they go to infinity they will be put to a limit by the predation. The more serious problem is this. Why? What is the problem there? BUV. Sorry? Nonlinear, of course. You would still have, even in the more realistic thing, you will still have nonlinear, but there is an assumption here.
They can't consistently keep killing. Right?
Exactly. So it's like going to a feast. Like I think I already used this example, right? One fish fantastic, two fish better, three fish wonderful. After the fifth fish, I'll really feel starting sick. Right? You give me 10 fishes, sorry, I won't be able to have it. Okay. So eventually, I will, even if I am a glutton, after some number, I will say I can't eat anymore. Okay. Right. So there is a saturation to how much prey I can have. Even if the prey population keeps going up, beyond that capacity, the number I am consuming has become a constant. Okay. So this essentially has to be modeled. So here what is the underlying assumption here is, if you double the prey, I will eat double. If I triple the prey, I will eat triple. If I make it 10 times, I will eat 10 times. Okay. That is clearly complete nonsense. Okay. So instead of that, what I can say is, so if this is how the population of the prey increases, then per capita consumption by the predator. So Lotka-Volterra is assuming that it is going up like this linearly. Okay. Instead of that, I could argue that it is actually saturating. So initially it is going up linearly, but after a while it is saturating. Okay.
V is the mass, right? It's not one.
Sorry?
It's V.
Yeah.
It's the mass of big axis. It's not one fish.
It is not one, it is the population, and so this is I am saying per capita, and so now I will be multiplying that with V in order to get the total consumption.
I'm saying that is the interpretation, that would it fall for the product of humanity? So it's like mass of prey multiplied, I thought the interpretation was mass of prey cross mass of predators. Like there is kind of like a matching which is happening at the
No, so what I am saying is that this is the amount that is being eaten by a single predator. So if there are V predators, this is the total amount which is being subtracted from the prey population. Okay, so the simplest way to model this is to say that you are not, so this is, let's say, BU. So you could say that actually you are going as BU by some quantity C plus U. Okay. How is this going to give rise to this? Well, when or rather let's call it 1 plus U actually best. So when U is very small compared to 1, so let's say U is actually it's a fractional number of something. Okay. When U is very small compared to 1, what happens? It's just BU, right? Because you can ignore U, so it's just BU by 1, so it's just BU. So it goes like this. When U is very large, it just goes to B. So, okay. So I could argue, so in general, I could write a C number. So I could say actually it goes as minus BU C plus U times V. Okay. All right. So now for dV dt, now I just have, so this is the consumption by the predator. So it will be the consumption by the predator times some efficiency factor epsilon, all right. And so this epsilon into B will, okay, sorry, I probably used a small c there. So I hope you won't confused with this capital C. Actually, maybe you know what, instead of capital C, let's call it A to avoid any confusion. Yeah, and then minus D into V, the death rate, okay. And so I can absorb this epsilon and B into a single number and call it like before C. So this is what I get, Cu by A plus U V minus dV. Okay. Is this the only way I can include saturation? No. Sorry?
We can do it like a carrying capacity per predator. They can eat a maximum of that BU, and depending on its carrying capacity, so keep kind of reducing. So we kind of get like how the population plateaus. Even this will plateau.
Well, I mean that's not too different from what's happening here, right? So you are saying initially I am just linearly increasing my consumption, but then I am saturating. No, there's another possibility, which is, suppose this is only one of the many goodies I have, okay. So I am not only a fish eater, I also eat like other things, okay. So everybody says Bengalis are great opportunists, right? So whenever you have this, like whenever in IISc we used to have these picnics, there would be some vegetarian and some non-vegetarian items made, and the Bengalis would first finish the non-vegetarian stuff and then attack the vegetarian stuff, right? So this was a constant gripe of the vegetarians. You Bengalis, you like opportunists, you are like, you eat everything.
They should first finish the vegetarian stuff.
There's a danger. Vegetarians, when pushed very hard, can become non-vegetarian. So no, you first want to finish the non-vegetarian stuff. Anyway, so now imagine that fish is available. My Bengali friends have finished all the fish. Okay, so what do I do? Or there's only a few fish left. Okay, so I'm not going to waste my time waiting for when the fish is going to arrive. Okay, I'm just going to attack the vegetarian stuff, right? So if I now look at how my behavior would be, assuming that I'm only looking at a particular prey, I'm not looking at the other kind of prey that I can work on. So when prey is low, I just don't bother. with finding it out. So my consumption is almost 0. But when prey is available in a sufficient number, my consumption rises until again my belly is full. Okay. So this is the so-called hyperbolic response function. So this is a linear response function, this is a hyperbolic response function, and this is a sigmoidal response function. Okay. So how do I model this? The simplest way is to just say that p u square by, let us say, 1 plus u square or some a plus u square. Okay. So this is per capita consumption. Okay. And so again I reach saturation, but here I now again also have a nonlinear growth. It's like a quadratic growth. Okay.
So I don't get what the problem is with the first assumption.
Because the first assumption is unrealistic. It says then
The RU.
RU.
Yeah. Like for the why you added the carrying capacity.
Oh yeah. So this is because, suppose now you are saying that what if there was no predator in the system? So then you are saying that basically
But then
this will diverge.
in many ecosystems, if you like if predators suddenly divert, the prey does explode and that like
Explode, but they can't go to infinity because of the finite carrying capacity of the environment.
But if it was self-regulated, then it would not be a problem if predators are not there. Then it's like
No, they will explode. But what will happen is that they will start fighting with each other, so that eventually, their population can plummet. But the idea is like it will eventually reach some kind of a finite thing. Whereas this is saying that it will just go to infinity. Okay, so that's the problem. Sorry,
Because why do we need a sigmoidal rotation?
I'm coming to just in the moment. Yeah.
No, I was thinking the prey food source is constant right here.
The prey.
The dependent on whatever food items like
So the example that I gave, you assume the grass is constant, or grass is like available in infinite amount. So grass is never not going out of thing, no matter how much prey is there. So you just keep eating the grass. But in reality, we know that there is only a finite amount of grass, which is what you model by the finite carrying capacity.
no, but prey can be dependent on something else, right? That can.
So that is modeled precisely by this carrying capacity. Okay. Which is why I brought in the carrying capacity, because you say that since the prey has some finite resource, it cannot grow unboundedly. Okay. So instead of explicitly modeling that food source, because then there is no end, right? What does grass depend on, and so on. So I have to stop somewhere. So I basically factor it into the carrying capacity. I say that there is only so much of the prey that can be carried by the environment given its finite resources. Okay, so coming back to your question about what's the difference between hyperbola and sigmoid? What do you think? First is, here we are talking about a specialist who can only feed on that particular prey. Whereas in the other case, sigmoid, we are talking about a generalist which can afford to not have this if it's too rare. If too much effort is involved in finding that particular prey, it will just switch to another prey. So we are talking about generalists here. Secondly, you have to have some kind of a cognitive capacity to distinguish between prey of one type and prey of another type. Okay. So you have some cognitive capacity by which you know that prey of this type is high in number, prey of this type is low in number, and so therefore you have the possibility to switch between one prey and another prey. So this type of behavior is typically seen for higher organisms, which have a minimum cognitive capacity. All right. Which behavior you will see often depends on the context. All right. So that's why you have to have some domain knowledge to know should you have a hyperbolic functional response. So this is also known as functional response. Okay, this type of how the amount consumed depends on the prey population. This is known as functional response. And after the ecologist Holling, so this is known as Holling type 2 functional response, and this is known as Holling type 3 functional response, while the linear Lotka-Volter is known as Halling type 1. Okay. Now, it is very interesting that there is a very nice analogy with how you have biochemical reactions which are cooperative. So, like if you have looked at Hill's equation, you would have come across this. Okay. So, if you look at, for example, what do you call the Michaelis-Menten equation. So, that is essentially like Halling type 2. Whereas, if you look at Hill equation with the Hill coefficient which is greater than 1, that is like Halling type 3. So, in fact, there is a very paper written sometime in the 1960s where an ecologist pointed out that there is this mathematical formal similarity between the way biochemical reactions take place, cooperative and non-cooperative, and the way you have Halling type 2 and Halling type 3 responses. Okay. The underlying mathematical structure is exactly the same. Yeah.
So it seems like you have these made products there, U into 1 minus U. But even if it's continuous, it would not have that bifurcation property.
It is continuous, so it will just slowly converge. In the absence of prey, it will just slowly converge to the carrying capacity. There is no chaos.
So that discrete and chaos.
No.
Because it's not.
Correct. Because it's just one dimensional differential equation. Yeah.
So the idea of higher cognitive ability sort of disappears when you bring in when you compare it with the chemical, the cooperative and non-cooperative interaction.
Yeah, so there is no high cognitive capacity, but this concept of cooperative. So does certain things become easier when something has already happened?
So it could be like in a spatial lattice, the more abundant one, which is well mixed, could be more. You came across this more frequently, so you consume it more, and the one which is lesser in population or concentration, you'll come across it in a less frequent manner, and you consume it lesser.
No, but see, in that case, here you will just die out, right? Because U is very low.
Concentration to bump into.
So this is basically saying that there is a possibility of prey switching.
Yeah.
If the possibility of prey switching was not there, you necessarily depend on that particular prey, then here you will just go extinct if you are a predator. Okay.
So here basically the sigmoidal takes into the, kind of takes into the picture where the predator is looking for the prey which is more abundant.
Yes, correct.
Both curves, the
So here what is happening is, as more and more prey become available, you consume more and more until your belly is full. Okay. Whereas here, since you have other food sources available and you can switch to them, you just don't bother with the rare food.
So if I want to interpret the saturation part,
Yeah.
which is saturating like ahead of the hyperbolic.
I'm not sure whether it's saturating the head of hyperbolic. That depends upon this, because this controls the slope.
Okay.
So it depends on this parameter. So by manipulating this parameter, you can make it saturate at different values. At what value of U you will start saturating, that can be manipulated by controlling this parameter. Yeah.
So, bees in a way, what are the chances of getting eaten by this predator?
Bee has lots of terms, but basically say what fraction of the prey a predator is basically consuming.
So, if the predator can switch, or whatever reason it is not eating this particular prey,
Yeah.
that will be taken care of bee, right? Why do you need a different kind of curve there?
No, that's because you are saying that if, that's another way you can interpret this. You can say that actually B is B into U by A plus U. Okay. Or something like that. Okay. So you can also think of it like that. Okay. That's just a question of interpretation.
Or did you just make B a function of U?
So if you can also interpret this by making B a function of U. Just as when I looked at the logistic equation, I showed that either you can say that, okay, I'm changing RU to RU into 1 minus U by K, but I can also think of it as RU times u, where Ru is a function of u such that it's R naught into 1 minus u by k. This is just a question of interpretation. Do you think of it as a b which is dependent on u, or just you are changing the functional form?
How do we know to add the square term?
Oh, square is not important. It could be cubic, it could be quadratic, or what, it could be a 4 to the power 4. It's basically anything which gives rise to a nonlinear curvature here. Just as the Hale coefficient need not be 2, right? In biochemical reactions, when you have cooperative reactions, such that, like for example, when you have protein, which when it's bound to something, okay, it is more likely to have another thing bound to it. So the reaction rates start depending upon whether already other stuff are bound to it. So you model it not like the typical Michaelis Menten, but as some to the power some Hale coefficient. And this Hale coefficient, if it is greater than 1, you get this sigmoidal kind of behavior, to the point you can, as the coefficient becomes bigger and bigger, you actually get a binary switch like behavior. So below that u, nothing; above that u, immediately like you go to full capacity, right?
I mean, suppose the thresholds are same. So like, how do you like explain the saturation which is happening faster compared to the hyperbolic?
Sorry, what do you mean? Saturation is happening faster?
Like it is saturating, I mean, way ahead than the hyperbolic.
No, but it need not be, right? Because I can control by this.
Yeah.
How fast or how slow I want to go to saturation.
Yeah, I mean, in case of hyperbolic, it's taking a lot of u, then it's
Well,
saturating.
again, by see here I have a, let's say, okay. By changing a is basically the value of u at which it becomes half of the maximum, right? So by changing a, I can make it steeper or more shallower and so on. So again, that's just a parameter. Okay.
No, I mean the rise part. I can understand that you said that it has options.
Yeah.
Yeah. But the convergence part.
Yeah.
So what is
No,
the
no, that's what
interpretation
I'm saying.
here?
If you change a,
Yeah.
okay, you can change the slope. So it can, because that's the value at which it reaches half of this per capita consumption. So depending upon where your a is located, here or here or here, it will rise like this or it will rise like this. Okay. So I'm free to control that depending upon my data. Okay. Okay, I'm basically out of time. I wanted to talk about a couple of other things, but thankfully for me, Shakti has already put up those reading materials. So you can just go and now look at these papers. So it's basically just to show that even though it was derived in the context of ecology, you can actually apply it to completely different domains. For example, history. So essentially you can think of it as follows. So there is resource, and this resource could be anything, mineral resources, food, whatever, and population. Okay. And so what is happening between them is basically resource is being fed up by the population and resource is being depleted by the population. Okay. So in a qualitatively similar way, you can think of it as basically like a predator-prey system. Okay. So there is a rate at which resource is renewing itself, but population is typically going to grow much faster, the typical Malthusian model. Okay. And this will result in something like this. So population rises. So as a result, you have a decline of the resource, and then population starts decaying. So then after some time, the resource starts recuperating again. So you have renewal of the resources, at which point the population suddenly realizes, hold on, there's a lot of resource, so we can rise up again, okay, and so on. So people have tried to, I mean, not exactly Lotka Volterra, I mean, that would again mean that historian is never going to speak to you again, but people have tried to use models of this sort to explain the cyclical behavior of, for example, the Chinese history. So if you look at Chinese history, it has this large empire starting with the Qin, and then you have like the Ming. I always forget whether the Ming is first or Tang is first. Anyway, so there is Qin, Ming, Tang, and then what was the last imperial dynasty? I completely forgot. The Manchu dynasty. So and so on, and then you have PRC, which is also an empire actually, if you think about it. So, and in between these, you have civic strife. So between the Manchu and the People's Republic of China, you had several warlords who had each separated China into their own fiefdoms and were like beating the shit out of each other, right? And so if you look at let's say civic strife versus population, it would show a behavior like this, okay. So Peter Turchin, and this is the paper that I have put in as a reading material, who is actually an ecologist. He has got a wonderful book on population dynamics, but then he realized this parallel between what he calls cliodynamics. As I said, Clio is the muse of history, so basically historical dynamics. So he said you can set up a mathematical models for these historical evolutions in the form, and so one of the models he has proposed is like this. So population goes as R naught n 1 minus n by carrying capacity, okay, and then he puts a variable here. I'll come to what that variable is in a moment, W, minus dn, and this has also this variable W. What this W is in a moment. Okay. Then state resource. So what state resources do is that it allows you to police people so that they don't start fighting with each other, and so this is kind of dependent upon what is your population. So if you have a lot of population, you can tax the population. So this is the revenue that you're getting from your population. So rho naught is basically the factor which says what is the per capita taxation minus the expenditure of the state. So assuming that your population is higher, you will have more expenditure, and so this is your expenditure, and then W is actually the internal warfare intensity. So people left to themselves would start scratching each other's eyes out. So this is what the state keeps in check. So an square, so bigger the population, so to have a fight you need two people, right? So what's the proportional of picking one? N. What's the proportional of picking the other? N. So it's n square minus BW. So in the absence of any population, hostility will just decline like this, and then the state resource is basically used to keep a check. So the police will come and stop two people from fighting. So the state resource is used to do this, and so now you understand what this W is for. So basically the more the internal warfare, the less the carrying capacity, and it also increases the death rate, okay. So Turchin basically so strictly speaking this is not a 2 variable model, this is a 3 variable model, but it actually shows oscillations, okay. And he tries to fit these parameters to, for example, various historical periods. Turchin actually has lots of popular books. One is called War, Peace and War, another is called End Times, and so on. There's also serious books he has written called Cliodynamics and so on. Sorry, you had a question?
See that the population consumes resources, so there is inhibition. That's the inhibition.
Yeah.
But at least over a long time scale, you can assume that population can also increase resources by improving efficiency. Right?
Yes. So this is strictly speaking an agrarian economy. Okay. So there's only so much vicinity of the earth. Okay. So very soon you reach some kind of a diminishing returns where you start, you can only have like much less fertile soil and so on. So this is strictly speaking the pre-industrial period of China, you might argue.
For time span which is this long,
Yeah.
this is probably centuries, right?
This is, yeah, 2 millennia.
Wouldn't you assume that that slow effect would have some effect and these dynamics won't?
Well, I mean, you have to take it with a pinch of salt. Yes. Okay. So there's a lot of, as you might expect, historians attack this with gutso. They think that this is like sacrilege, trying to make a mathematical mockery out of history. So, but I think we are in the same stage as what mathematical biology was, let's say in the 1910s or something, when population genetics was first starting out, right? Yeah.
So you think this model shows oscillation?
Yeah.
So, but like one of the variables is population, and population increases.
No, but population is kept in check by the fact that you have a carrying capacity, which gets reduced by because there is more population that is there, the more internal warfare intensity rises.
Yeah, but in the real world, the population increases monotonically.
No, but see, if as population exceeds the resource, okay, what will happen? They will start fighting with each other.
Yeah, but like, I mean, has the population ever decreased significantly due to?
I mean, tons of times. Actually, Europe almost came to complete extinction because of the Black Death, when the Mongols attacked them.
Like because of like epidemic deaths, because of wars. Like,
No, but how did that Black Death start? It was because of biological warfare by the Mongols, right? The Mongols basically threw infected bodies into these fortresses through catapults, and that's how Black Death basically spread into Europe.
So, like China's population right now is some like 1.4 billion.
No, we have crossed it. India is now the most populous country.
But like in what point in the past was it that high? But I thought I was like
No, it's true that you are getting more efficient at how much. So you could argue that these peaks are getting larger and larger, but eventually, you're reaching some kind of a limit set by your ability to extract out of the resources, at which point people start fighting with each other. Okay, all right. Okay, so I really should stop now, just to say that there is another model called Goodwin model, which basically tries to model the boom and bust in economy. So if you look at typical economy, there will be a period of inflation followed by deflation and so on, and many people have tried to model this kind of endogenous oscillations, and in the Goodwin model he basically uses two variables. One is the labor share of GDP of a country's income, and V is the employment ratio, that is what is the out of the total labor force how much is employed, and then he basically sets it up sort of like a Lotka-Volterra model. So you can just look up Goodwin model and you will see that this is actually mathematically very similar to the Lotka-Volterra formulation, and this basically tells you why you have this boom bust kind of cycles. All right. Sorry Shagor, can I just take 5 minutes and I'll just so just because I promised everyone that I'll show you a bit of chaos. I mean, already the lectures are pretty chaotic, but so now what happens? Okay, so you notice that once you went to 2D, something more than just equilibria and divergence became possible, right? Namely, you got oscillations, right? And the reason is that whereas in the line you could not get oscillation, because that would meant at the same point you would have to have one vector pointing this way and one vector pointing this way, which is not allowed. Similarly, in a plane, in order to see anything, so this is fine because everywhere you have only a single arrow, but you want to have something which looks like this, you can't, because wherever you cross you will get in trouble. But now once you go to 3D, this problem is removed. Okay. So let me just, since I have always been using ecological systems, let me tell you about another ecological system. So this is a 3 species food chain. So what I am going to do is I am going to take something like this modified Lotka-Volterra that I told you about and turn it into a 3 species system. So I have a prey, I have a predator, and then I have a super predator. So my dx dt would be again r x into 1 minus x by k minus, and I am taking Halling type 2 functional response. So c1 x by b1 plus x. Then my predator equation would be dy dt a2 xy, sorry, this would be y, a2 xy b1 plus x minus, now this is the predation because of the meta super predator, a2 yz b2 plus y minus the death rate, and finally dz dt equal to c2 yz by b2 plus y minus d2z. Okay. Now this has like so many parameters that you realize that one can't really reasonably go through the parameter space, so you have to non-dimensionalize, just as I non-dimensionalized a 2D example, okay, before, sorry, a 1D example when we looked at the imperfect bifurcation. So if you non-dimensionalize and do the proper replacements, you can get a much simpler equation which looks like this: x 1 minus x minus a1 x by 1 plus b2 x y dy dt equal to a1 x by 1 plus b1 x y minus a2 a2 y z by 1 plus b2 y, and then minus d1 y, and then finally dz dt equal to a1 y, sorry, a2 y z by 1 plus b2 y minus d2 z. And this, it turns out, is capable of showing chaotic behavior. So if you plot so this is my x, this is my y, this is my z. So this shows a behavior something like this. So you have, so this is not crossing each other because this is just, this is happening in 3D, right. So if you look at a section, it looks as if these curves are crossing each other, but actually they are forming this kind of a spiral kind of behavior. So again and again they start getting injected and then go back again. So they never quite repeat themselves, okay, and this can go on forever. Okay. Now the question often is, okay, how do you measure the degree of chaos, and okay, what is meant by chaos? So chaos is actually, so you can argue that chaos is a bit like, you know, irregularity or unpredictability, but technically what we mean by chaos is sensitive dependence to initial conditions, or the so called butterfly effect. So chaos is marked by sensitive dependence to initial conditions, what is colloquially known as the butterfly effect. That is, a butterfly flapping its wings on the Atlantic can cause some changes which gradually amplify their effect, so that there will be a tornado in the Pacific. Okay. So, what this means in terms of this is that, suppose you start from here, okay, and you get a trajectory which looks like this. Something like this, and then you take another trajectory which starts from very close by point. Okay. So, initially you expect them to more or less follow each other, but very soon they will start diverging and you could get a behavior very different. So, even though it looks like the same trajectory, basically what you are showing is that the time series, if you look at, would look extremely different. So, in one case, let us say the trajectory would go like this. In the other case, so you start very close by, but then they are completely going very different and so on. Okay. And how do you actually quantify this? So, this is quantified by something known as the Lyapunov exponent, which basically asks that if you start two trajectories, one at x naught and one at x naught plus delta x, then after very long times, when this is x t, so and this is x prime t, so the question is what will happen to this delta x. Okay. So, the idea is that delta x at time t, the deviation from the neighboring trajectory would go as delta x naught e to the power lambda t, where if lambda is positive, that means these two trajectories are basically diverging like this, and you are measuring basically this rate of divergence, how quickly it is diverging. Whereas, if lambda is negative, it means that the two trajectories are actually going to converge. And so, you are measuring, okay, how quickly do they converge. What will happen when lambda equal to 0? Well,
Fixed point.
well, first you no, not fixed point. Well, you might think, oh, there is no difference, that they maintain a constant difference. It just means that any divergence is less fast than exponential. Let us say a power law growth. Okay. There can be a power law divergence, like, but it will not come out as a exponential divergence. So, lambda will basically be 0, but that does not mean there will not be any divergence. There could be a slow divergence. Okay. All right. So, with that, let me end here. There are reading materials, please look them up, and I am always available if you have any questions about this dynamical system. There are a few other things I wanted to try out, but I am pretty sure Shagor is going to cover discrete dynamics in his, no? Okay, does not matter. Does not matter, we can always have a impromptu session during one of these. Yeah, we will have an impromptu session in one of these, you know, after class meetings. Okay. All right. So, with that, I will finish my course of lectures.